Okay, Don. I sincerely apologize for taking so long to get this to you. No good reason, just it's been a difficult time to put this on the front burner, but we definitely owe it to you to get this going. Alright, this is how we test motors in 360. I'll be sending you data files that correspond to data that I took using this particular test stand, this setup, pair motor. This is the actual motor itself. This is actually what we call a dynamometer. But I'll be sending you data. Today I'm going to show you the procedure, or through this movie I'll be showing you the procedure as to how we take the data. Now, what we've got is the motor itself is fixed to this assembly. We have a DC power supply over here, but the motor is fixed in here. It has a shaft that's inside some nice bearings. We have a nice little shaft coupling in here. We updated them. We used to use Lovejoys. I don't know if you're familiar with those. They've got that kind of spider gear rubber between them, and as they go around, and really made it a nightmare. But I'm pleased we went to some solid type, but they're those pieces of aluminum that have got the sort of spirals cut in them in multiple places. Anyways, it's improved substantially since then, a few years back. What we also have here, we've covered it up with blue tape just to give it a nice background that's not reflective. And then we put on a little piece of reflective tape there. We use that to measure the speed using a handheld. Here we go. Using a handheld tachometer. This is an X-Tech 461920 handheld tachometer. What happens is if we shine the dot, there we go, on that spot as it's spinning, then we can actually get a measure of the RPM. So I guess to that end, why don't I go ahead and rev up the voltage here. And just to demonstrate how we can do that. Now this is in counting mode. If we know the amount of time and then the elapsed time for 190 revolutions, then we can do it that way. Alternatively, we can just measure it directly with the RPM. And we get a little bit of noise in there. Right now it seems to be 15, 41, 42. That's pretty steady. 43, 44, 45, 44, 45, 46, 47. Alright, so much for steady. But it's in the vicinity of 15, 46, that's 45, 44, 43. So we might call that 1,545 RPM. The voltage right now is running about 13.4 volts. The truth is I would not actually use the output of the power supply to measure the voltage. I would take a digital multimeter and I would directly measure the voltage down here. The reason why is that this power supply is a relatively economical power supply, shall we say. I don't know that I trust it, and also it doesn't give us the accuracy perhaps that we might get off of the digital multimeter. Now, other elements of this assembly. This is actually the dynamometer. You'll notice this is actually free to spin. It's essentially a DC motor. Not essentially, it is a DC motor. And the leads of the motor are actually left open right now. And so what you'll see is we have a load cell here as well. But what you see is there's really very little torque that's produced there. So what's happening is the motor is spinning in this right here. I think I have it backwards. No, I don't. I have it in the right direction. Good. Motor spinning in this direction, and it's trying to push this this other housing down here, but the housings, there's very little torque generated between the rotor inside this motor because we allow no path for the current flow. Remember, we've got permanent magnets inside here, so it's a permanent magnet DC motor. And we've got an armature that's spinning, so we're taking these coils and we're spinning them in the presence of a magnetic field, which should produce a voltage which we could measure across here. We can. I don't have a good handheld meter to do that with right now, but if we measured it, we could see it. Well, let me go ahead and hook that up. As they say, no time like the present, right? So here we go. Hook up our digital multimeter. It's a pretty nice one. We'll put it to measure DC volts, and is on auto rating right now. And probably what we'll do is we'll measure something of an oscillating value here. It's measuring on the order of 11.6 volts. Interesting that I'm driving with 13.4. It's a slightly different model number of a generator than it is of the motor. That's to say the motor that we're using as a generator is slightly different from the motor that we're using as a drive. But we're generating about 11.6 volts. As we slow it down, now I've got 8.4 volts going in. My generator is producing about 6.8 volts coming out. Now, keep in mind, there is a trickle of current. We're talking microamps, I suppose, going in this lead into the meter and coming out the other side. If I go ahead, though, and this is the interesting part, and I short these leads, let's see what happens. So I'm going to bring it back up to what I think is approximately 12 volts. And again, were I taking the data today, I would disconnect these and I would directly measure it. So my DMM tells me that I'm actually putting out 11.97 volts. So I could either adjust it just a little bit to get myself 12, or I could go ahead and live with my 11.97. Now, check this out. When we go ahead and do this part, I'll do like I do with soldering. I use one pair of fingers for that. Maybe I use this pair, and I can. You'll notice something happens here. Maybe you can see this, and maybe you can't. Right now on the power supply, I have about 0.9 amps of current going through there. As I shut these, I go up to 4.1 amps of current. And what's happening is I'm actually shorting the leads on the generator. As I do that, current then flows through that armature. You've got coils rotating in the presence of a magnetic field. That produces a voltage. If I give the voltage a path to go through, then now we've got the resistance of the motor. A little spark there too. The resistance of the motor, and that's producing current. Now we have current traveling through coils that are in the presence of a magnetic field that generates torque. And it turns out the torque is going to be in opposition to what you're driving it with. Now, like I said, 4.1 amps over there. One of the interesting pieces of the behavior now is you'll see it's got a very different, I should probably do that to the power supply, but it takes a fair amount of effort now. I know it's not a lot, but I can go ahead and push on it now. But it's obviously, it's snapping back on me a little bit. Whereas before, there's very little torque, so it's being driven on that. That's the general approach of this. Now, what we do is we want to provide varying torques. The most torque, let's suppose we drive this thing with 12 volts, approximately 12 volts. The most torque that this generator can put out is to shunt these two directly together. Because the equivalent resistance, we've got approximately 12 volts being generated inside that generator. When we shunt these, we have zero external load resistance, zero. But the internal load resistance, I guess we should probably find out. Let's go ahead and find out what it is. Now this is not relevant, it is relevant to your understanding, but it's not relevant to the lab itself. That is to say, you don't do this in calculations in the lab. Okay, looks like I got about 2 ohms of resistance on this generator. Now one thing I might want to do is turn the shaft. Now all of a sudden I got 6 point something ohms. And I turn the shaft a little more and I got 3.5. And I turn it again, I've got 4.3. And I turn it again, I got 5, 6, 7. I saw 7 for a moment. I might have even seen 8, but it varies. And what's happening is you've got commutators there. As we run around, we're engaging more or less numbers of coils, a higher or lower number of coils, if you will, going around the armature. So we do, I don't think it's safe to say there's a fixed resistance to this motor. It does have some nominal resistance, but it'll change as a function of position slightly, I believe. I'm not a motor specialist here, but that's based on some years of observations on this. My point is, if we shunt this, we'll have the greatest amount of torque because we have the smallest amount of resistance inside the motor, the generator itself. As the resistance gets larger, though, the generator puts out the same voltage at a given speed. Okay, so if it was putting out 12 volts and we shunt it directly, a couple of things happen. One is we're not going to be putting out 12 volts anymore. Let's suppose that we did, for an instant, we put out 12 volts. Let's suppose that we had 6 ohms of resistance in there. 12 volts, 6 ohms, we get 2 amps of current flowing through that device. That's a pretty healthy amount of torque that we're going to produce out of this motor. As it produces a back torque on the motor, which is being driven with, actually in this case, 12 volts, and I think I said this produces 12. I'm sorry, that's more like, we will have to check it and see, but the point is it's some fixed voltage. As we get the current going through that, that produces back torque on this. This thing is operating at 12 volts with no torque. It gets a certain speed. We said 1545 RPM or so. Maybe that was a 13 volts. The speed will drop. That's the point. It's still being driven with the same voltage, but the load is increased. And so if we look at our DC motor curves, we're actually coming down the curve with load, but if we're at it, we're actually pretty close. This is speed on the x-axis, and we got torque on the y-axis. We're pretty close to that no load operating condition for 12 volts. For 12 volts, there should be a line here that goes between torque and speed. As we increase the load, our speed will drop. All right? So it will find a new equilibrium position where it's producing, because there'll be less back EMF in here. Yes, we applied 12 volts to it, but not all that voltage gets converted to current across the motor resistance. Some of it is converted to back EMF. The bulk of it is converted to back EMF in this case, at the no load situation. In a perfect world, all of it is converted to back EMF, and zero current is available in there. Zero voltage is available to produce current, which then produces torque. Now, as we slow it down by applying a torque to it, then the back EMF will go down. Maybe it goes down to 8 volts or something like that. And again, that's internal to the motor. We don't see that, okay? But that's the equivalent voltage that's being dropped over the resistance of the motor. As that voltage, let's see, the back EMF goes down, so the voltage being dropped over the resistance is what I'm trying to say, it goes up, which means our current will go up. At the no load condition, we had essentially 0 amps. As we provide a torque to slow it down, the motor will respond by the current going up some. Now, in it's finding a new equilibrium. That's the whole point. And we can discuss this more. I think we're going to have some phone conversations and such, which is perfectly good. We can do that. Now, what's happening over here is this will be driven at a lower speed. It's true. It will produce less torque as well, but again, we'll come to an equilibrium point where the torque produced here balances the torque produced by the motor, and the torque produced by the motor is, again, this function of an equilibrium of how much torque have you got coming back, how much applied voltage have you got over here. So to find an operating point on that curve. Now, how do we find different operating points on that curve? Well, we produce different amounts of torque here. The maximum torque is going to be produced with the minimum load resistance, which is internal to the motor. Okay, that's when we shunt it like this. If we want to go ahead and maybe produce less torque at a given speed or a given operating condition, we can use these. These are 4 ohm resistors, I believe. Let's see, 120 watt 4 ohms. This is a 4 ohm resistor, 4, 4, 4, 4. Okay, if I put them all in series, I go this one connected to that end, this one connected to that end, this one connected to that, this connected to that, then I get 20 ohms of resistance. So if I do that, I can, and right now it's not hooked up in that fashion. Let's see. Right now, these two are in parallel, these two are in parallel, and these are in parallel out there. This one is not actually in use, this middle one. Okay, so right now I've got 1, 2, 3, 4 of them in parallel. If they're 4 ohms each, 4 ohms in parallel should give us about 1 ohm resistance. We can go ahead and check that one as well, right? We've got the device, we can do that. As they said in the $6 million man, I almost said 7 million, that was Barney, he was the $7 million one. The $6 million man was Steve Austin, but as they said in that intro, we have the technology. There we go, 1.177 ohms, 176, 175, approximately 1 ohm. Doesn't really matter. The point is, we're adding an ohm of resistance to the motor. to the generator. So by adding an ohm of resistance, let's go ahead and crank it up again. Now I'm going to find a 12 volt operating condition. I know I said not to pay attention to the chart, to the meter up here, but let's just use it anyways. So at 12 volts applied to the motor, to the drive motor, looks like we're getting a pretty steady 1390 RPM, which is an invitation for it to change, and it just did 91, 92, 92, 91. So let's call it 1391 RPM. Okay? Now, I'm going to go ahead and take this, and I'm going to shunt it with 1 ohm. And I don't know if it comes through in the audio there. What you can do is we'll see a number of things happen. We're going to watch the current is at 0.9 amps. Current went up to 3.3 amps, and the speed went down. We're at 935.6 RPM, 937.7, 38.8, 37.8, 39, 38.6. So let's call it 938 RPM. 12 volts applied to the motor. That didn't change any. What we did is we shunted the generator, and I can feel more torque produced there. Okay? If 1 ohm did that, what would perhaps 4 ohms do? That's one of the things that a lot of students make mistakes on, is that what will happen is they think that by increasing the resistance, they'll be increasing the drag. Well, let's go ahead and decrease the resistance, increase. So I had 3 of these in parallel with the last one, so that was 4 4 ohms in parallel to make approximately 1 ohm. Now I got a single one of them. My current went down to 2.2 amps on my drive motor. My speed is now 1117, pretty solid 1117. Again, it's an invitation to change. 1118, 1117. So we could call it 1117.5 RPM. And I don't have as much torque, and I know it's hard for you to see probably, but I can feel it as I push on that. So the point is, what we do is we adjust the load that we apply to the generator in let's just take a look at 2 limiting situations. The one limiting situation that tells you the relationship between load resistance on the generator and the torque produced by the generator is the concept of infinite resistance. If we have infinite resistance, well, how do we do that? Open it up. We've opened up the leads. Our current goes down again 0.9 amps, 0.8 amps. Our speed should go back up to approximately, what would we say, 1345? 1402, 1401, maybe I said 1395, I don't know, 1401 right now. So our speed is going up considerably. Yeah, I've got the other one connected, but it doesn't matter. It's not important. So by varying different loads at a fixed voltage and measuring the torque and measuring the speed, then we get an idea of how this motor works. So let's go through those measurements. I just alluded to measuring torque and speed. I've shown you how to measure speed. That's done. I'm showing you how we vary the load there. The last one is torque. How we measure torque. Well, you may recognize this, you may not. I don't remember if I sent you a load cell to look kind of like that, but this is one of those interface load cells. It's about a 10-pound load cell. It's actually being pushed on in this direction, and so if we put a circuit together, an instrumentation amp circuit, we actually can measure the force produced at the end of this moment arm. Key point there. That's the moment arm. There's a force out here which corresponds to a torque. So the data that I'm going to send you, actually I've gone and done some of the data. First off, I calibrated. The very first thing I always do when I do this experiment, I've done it a number of times, I actually calibrate my load cell. I take it out of the test stand, put it on the end of the bench. I have a bunch of brass weights like the ones that I sent you. Put on the weights one after another, get my force versus weight curve. Then I got my calibration of the load cell. We put it back in here. It has a different zero, so it's very important. That's one of the key pieces of data that a lot of students make a mistake on. I'm going to give you the data already in terms of force versus speed we've got out of there. But the concept is it is in a different configuration. It's horizontal now. It's got a different offset. So we would actually have to go ahead and rotate this away from the load cell with no motor applied. Let's turn our voltage off. So we rotate that away. We would now take the measurement of the load cell voltage. That would be our offset, or our zero. Then we gently rotate this over. We crank up our speed, not our speed, our voltage. And this time I'll do it right. Go ahead and say, hey, are we really doing, let's see if I got my voltage here. Ten 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, not yet, 9. Hey, that's pretty good. 12.016, 12.018 volts. So I measure my voltage there. I have no load applied to the motor. I can go ahead and measure the speed. This data point I really wouldn't use because it's not a no load speed truly. There is load applied there, but we do have friction in those things. But that's to show you how it works. So we do 1392. At that point, I take this and I hook these up to my resistors. After having set the resistors, maybe I put all 5 in series. That gives me 20 ohms of resistance. I hook this up, I'll find that it doesn't change the speed a lot. 20 ohms is an awful lot of resistance. Then I go ahead and bring it down to maybe 4 of them in series to 16 ohms. And I forget the actual numbers, but it might have been 20, 16, 12, and we go down, we get to 8, of course, 4, and then to get 2 ohms, we take 2 of them in parallel. And then we get 4 ohms, we go 1, 2, 3, 4 of them in parallel. Usually we trim down some of those. There's not a lot of point to take a data at the 20 ohm load. It doesn't change a lot from the open circuit condition. But while I'm at 12 volts, I take all that data. I take it with Signal Express. You've been using the little USB oscilloscope. We have data acquisition cards in the computers here in the lab that will take a long time history of data. What we'll find is that there's not a clear value on the load cell. It actually has vibration. I can hear the vibration. Maybe you can too in the video, but it's got some oscillation there. What we do is we take maybe 5 seconds of data at 10 kilohertz. It's a lot of data points, 50,000 data points. Then we take the average out of all that. We take that average value, and you can look into the raw data. I will be sending you raw data. But then we take that. That average value is going to be pretty representative of the average force on a load cell. We take that voltage, we convert it through the load cell calibration curve, knowing our zero. We convert that because we get the sensitivity off of the regular calibration. Then we look at our 0 point, look at voltages away from that zero, and the sensitivity that tells us how many pounds we got on the load cell. At that point, we actually will have measured, I forgot that minor detail, we actually try to make a good measurement of this distance here in inches or in millimeters or centimeters, however you want to look at it, to get the moment arm. Using those two together, we can get the torque at this point. Again, we make that kind of measurement once for the test. We make the load cell calibration once for the test. The general procedure, though, is turn it to a fixed voltage, record our zero, because things do drift a little bit in the lab, but we record a zero on the load cell, take the resistors, apply 20, 16, 12, so on and so forth, all the way down to 1 ohm. At each one of those instances, we measure the speed, and we measure the torque for, say, 5 seconds, so that at every voltage that we have an input, we've got a corresponding 5 or 6 load conditions. So maybe this will be my voltage. I got 5 or 6 load conditions. I think I did 6 myself when I did it because I had a total of 18 data points. And then we're done with that voltage. Now what do? Well, we crank it on up. Let's pretend that I cranked it up to 18 volts, so now I've got 18 volts up there. Now I go ahead and I make my measurements again. Don't see an awful lot of torque there right now, but now I do. I'm getting a pretty substantial. I mean, it's taken some amount of effort now to do that, to get that coming through. We see 6 amps of current going through. So the point is, we do that again for 18 volts. We run through the 6 different load conditions, crank the voltage up some more, maybe go up to 21 volts. Or crazy enough, then we go to 24. Looks good to me. Maybe I shouldn't record this one for posterity's sake. 8 amps of current. Oh yeah, oh yeah. Let's see if I can do it with my pinky now. I can, but you can see the little white stain around the fingertips there where I'm pushing the blood out of there or whatever. That's taken a certain amount of effort to do. So we tested at these different load conditions. When you're all done with the test, what you got are actual, all right, raw data is the voltage of the load cell and the speed of the shaft you're coupling it to a motor and a generator at a given voltage at a set of resistances. We then do it for another voltage, the same sets of resistances. The resistances themselves don't matter. What matters is they will create variable loads with the generator. We don't actually have to determine what those loads are, except we measure them directly with a load cell, on the load cell, the moment arm, and its sensitivity of the load cell. So again, the raw data is 6 maybe pieces of load that correspond to, of course, the 6 different resistance values, but it doesn't matter what those resistances are. But we have 6 load conditions and 1 drive voltage and 1 speed. And we do that times 3, okay? And I said that wrong, I'm sorry. For 1 voltage, we have 6 load conditions, which will correspond to, again, 1 load voltage, that's a piece of raw data, and then we have 6 pairs of speed and torque, or voltage coming off the load cell. Plus, we'd have to have the raw data of the 0 offset of load cell, and then we'd have to know the sensitivity. After we take all the data and we go home and we play with our spreadsheet, what we end up with are 18 data points, 6 each for each of 3 different voltages applied to the motor. So I think I might have done 6, 12, and 18. I'll check the data. It might have been 5, 10, or 15. I try to do them in combinations like that. At each voltage, I have 6 measurements of speed in RPM, and I have 6 measurements of torque in foot-pounds. Then I go through using what I know about DC motors, and I try to determine what the motor torque curves are. I do a curve fit, and I find out where the x-intercept is. I call that my no-load speed. So now I know what the no-load speed is at a given voltage. That gives me the back EMF, because back EMF is measured in volts per speed, be it RPM or radius per second, or however you want to do it. I also go over and I get my torque, my stall torque. I don't so much need that, but as soon as I have the data points and my no-load speed, because once I know my no-load speed, I know my back EMF constant. Once I know my back EMF constant in the metric system, then I know my torque constant in the English system. I can then do some curve fits, and again, I'll get out resistance of the motor to go along with that as well. So those are the 3 parameters we're looking for. Torque constant, which is essentially back EMF constant, and also motor resistance. What we're saying is, I wonder what the resistance is of this motor. We then compare that to data from the manufacturer, and I'm sending you that data file as well, or a little piece of data sheet, I should say. And that's what we get. So that's about DC motors. I've wandered a bit in my presentation here. I hope it's still recording. I've never done a recording with a Surface before, but let's find out. So I hope this it gives you a good intro. We can do it again. I'll leave it set up, and if this doesn't work out, I have an obligation to you to do this again. We'll get it right. So I'm going to send you the data. I'm going to send you this file. The problem with the file on Dropbox is so big. But I guess that's, if you're watching this, then it worked. Thanks. Bye. Ouch. Stiff knee.